In this VoxCAD tutorial, I'm going to show you a little more about the advanced physics simulation that you can do in the physics sandbox. So first of all, I'll note that when we go File Open, this opens just the voxel geometry. We can also import a simulation file, or VXA file, that contains not only the voxel information, but also information about the environment and the simulation parameters. So here I'm going to open this guy. You can see we have a little ball and a hoop here. And when we go into physics sandbox mode, we can see a few things. First off, we can still click and play with things, but now I've defined the bottom of this hoop to be fixed. But this ball here doesn't have any external constraints on it, so it's allowed to float and bounce around here. So let's look at a few of the parameters here. We've already seen that we can look at, say, internal strains, displacements. Let's leave it on strain for now. But what do these things do? So first off, the time step. If we make the time step very small, the simulation goes a little slower but is very stable. If we make the time step larger than we guess, you can see eventually the simulation will blow up. So if that ever happens, no big deal, just turn it back down, reset, and restart the simulation. So that's the time step. The bond damping ratio defines how much each adjacent voxel is damped relative to each other. So if we turn this down, you can see we start to get a lot more jiggle between bonds. This also tends to make it less stable. So for most purposes, you can just leave the bond damping ratio turned up. The ground damping ratio, or can also be called fluid damping, damps each voxel relative to ground. So here with no ground damping, it's like we're in air, but as we turn up this damping ratio, it becomes more and more like we're in fluid. So you can see here it's sort of a damping proportional to velocity. So let's leave ourselves sort of in an air-like setup. The collision damping, like you would expect, defines how much each collision gets damped out. So here with no damping, our little ball will bounce. With high damping, the ball will just kind of stick. So again, here with high damping, very inelastic collision. There's a checkbox here to enable self-collision. So you can see now this ball, if I try to roll it into the hoop, bounces off like you would expect. This can be a performance hit with large models. So in some situations, it doesn't really matter, so you can turn off self-collision and the simulation runs a little faster, but without calculating those collisions. So in our environment variables, we'll go to the temperatures in a minute. We can turn off gravity. Does just like you would expect. We can turn the floor on and off. So without the floor, our little ball here can go underneath, just like you would expect. Turn both of them back on. At any point, we can go to the Trace tab here, and now I've selected I want to view displacement of my highlighted voxel in purple in the X direction, and this trace here shows what that's actually doing in absolute units. So displacement is in meters, and force is in newtons. This is internal force. Finally, the last tab here, output, tells you what the time step is and how many simulation time steps are happening per second on your computer. So real quick, let's go back to this temperature setup. So first I'm going to import another file here. And then when we set up these materials, I've set up this blue material to have a certain stiffness, but also a non-zero coefficient of thermal expansion. So in this case it's negative. Our red material has a positive coefficient of thermal expansion, and our yellow material has no thermal expansion. And we're also setting friction here. So for instance, a static coefficient of friction of 1, dynamic coefficient of friction. This is a normal sort of stick-slip friction model. And now when we import into our simulation model, I've set it up so that the temperature is varying sinusoidally. So let's look at the materials here. So both the blue and the red are changing size as my environment is changing temperature. So if I turn off the varying temperature real quick, you can see that as I change the temperature from low to high, based on the coefficient of thermal expansion that I set, these materials actually change volume. So this is one way to provide actuation. And when I click vary temperature, it sinusoidally varies that temperature with the period that I select here. So here, very slow. So move this down a little bit faster. So this allows you to do periodic actuation, and you can see this guy is actually sort of walking a little bit as well. So that's a brief intro. All the physics simulation going on underneath here is the VoxCAD physics simulator, and this is all available as its own separate SDK that can be incorporated into your own programs.